Hello everyone, and welcome to Things You Should Remember from Strength and Materials, but have likely forgotten. I'm going to start with shear and bending moment diagrams, and this is the example that I will be going over. Pause here, try to go through it as much as you can, and then continue the video so that you can confirm your solution against mine. All of my solutions have been done beforehand. Everything you will see here is screenshots, just so I can go quicker through it, and you guys can pause, rewind, rewatch as many times as you need. So starting with this, we get our diagram, and from here we have to find our reactions at A and D. First things first, we need to take that distributed load, the 15 kilonewton per meter on the right, and bring it into a point load so we can do our statics equations. The way we do that is we take the area on the top left, 15 kilonewton per meter multiplied by 1 meter is a total of 15 kilonewtons. That is applied to the centroid of the shape made by that distributed load. In our case, it's a rectangle on the left, so it will be exactly in the middle. In the case of a triangle, just for reference sake, it will be, the centroid will be 1/3 from the larger side, or 2/3 from the smaller side. And so we get the equivalent load of 15 kilonewtons halfway through that distributed load, so half a meter from the right side of the beam. And so from here, we can get into our equations. We should confirm that AX is in fact 0. In this case it is, because there is no other load in the horizontal axis, but it's always good to confirm and to acknowledge that A is capable of having a reaction force in the horizontal axis. And then we start with our sum of Fy, with up being positive. AY and DY we assume to be positive, and we have our loads totaling up to 31 kilonewton going down, denoted by the negative. Since up we denote it as positive, our total loads will be negative. Since we have two unknowns, we need another equation in order to solve for AY and DY. And so we have moments about A summing up to 0. You can pick any point here at this point to take the moments about. I just picked A. And so we have our, going counterclockwise is positive. And so we have our first load, -8 times 1, because that's producing a clockwise moment about A. We denote that as negative. Same with our second 8 multiplied by the 2 meters, because it's 2 meters away from A. And then also with our 15 kilonewton load at 3.5 meters away, all those are creating a clockwise rotation, therefore opposite of what we've called positive. We have dy times 3 because that is 3 meters away, and it will be producing a counterclockwise reaction, or a counterclockwise rotation, therefore positive. And then we also have to include our 20 kilonewton meter that is applied in the middle of our beam. It doesn't matter where it's applied, it's already in kilonewton times meters, so we don't need to multiply it by another distance. Rearranging and doing a quick bit of algebra, we find that dy is 32.167 kilonewtons up. During our math, we got dy being a positive number. Since we called up being positive, since it's positive, it is going upwards. And from there, we can substitute that into our Fy equation. Rearranging, we get Ay to be -1.167. We assumed it was upwards. We made a wrong assumption. What we do is we change Ay in our diagram to the top left to be going down. So Ay is 1.167 kilonewtons going down. And now that we have all of our reactions and all of our loads considered, we can begin building our shear diagram. In the top right is how we denote what's positive and what's negative. This is what you'll see most commonly, going from left to right. I read from left to right, so I like to go across the beam from left to right. And so we start with our first load. That section in the bottom right is technically infinitely small. The distance from left to right will not matter. What I'm trying to show is that we are only taking a section of the beam before that first 8 kilonewton load. And we see our only load on it is AY, pulling down by 1.167 kilonewtons. And so in order to remain static, our reaction, the reaction that's internal in the beam, is 1.167 kilonewtons going up. This makes the entire beam static. Sum of forces in Y equals 0. The reaction in the red is up. The diagram in the top right denotes what's positive and what's negative. It says the reaction going down would be positive. Since this reaction is going up, its opposite, it is denoted as negative in our shear diagram. Moving along, we reach our 8 kilonewton down load, and so we do a similar sum of Fy, and we see that our reaction is up by 9.167 kilonewtons. Again, still up, still opposite of what we call positive, and so we go down to negative 9.167 kilonewtons on our shear diagram. Moving to our next load at the 8 kilonewton mark, or the 2 meter mark rather, another 8 kilonewtons. Again, we do the same thing, sum of forces, and we get our reaction to be up 17.167, opposite of positive, so our diagram goes down to negative 17.167. At this point, we have dy coming into effect. dy going up at 32.167 kilonewtons counteracts all of our loads going down and then some. When we do the sum of Fy, we see that the internal reaction done by the beam is down now. It's down at 15 kilonewtons. Down, meaning positive, based on our sign convention in our top right. And so we go up to a positive 15 kilonewtons on our shear diagram. Now the tricky part is now we have a distributed load. That distributed load is a constant 15 kilonewtons per meter across the full meter that the load is distributed. So for the first little bit, we're going to have a little bit of force. When we get halfway, we'll have 7.5 kilonewtons of force, and when we get all the way to the end, we'll have the full 15 kilonewtons of force going down. And so this isn't going to be a flat line. It's not going to be reflected as a flat line on our shear diagram. We actually see a triangle going down at a constant slope of 15 kilonewtons per meter across 1 meter, bringing us to 0. It is important to note that since there is no reaction at the very end of the beam, there's no extra load, that there is no shear force left. There is no internal shear force left because there's nothing else to react to. This is an important note so that you know when it should be equal to 0 and when it shouldn't be. On the left, we had the reaction at A, and that had a non-zero value, so we start at a non-zero value, but we finish at a 0 value. Now from here, we can build our bending moment diagram. We still keep the same sign convention in the top right, where the positive is denoted by a reaction going counterclockwise. That isn't really, how do I put this? How do I put it? That doesn't really come into play until we have a direct moment applied, because the easiest way to do it is to take the area from our shear diagram and plot that. So A1, that little rectangle on the left, the negative 1.167 multiplied by the 1 meter gets us negative 1.167 kilonewton meters. And so our our bending moment diagram starts at 0 and ends at negative 1.167. If we imagine us going along the x-axis on our shear diagram, that A1 is getting a little bit longer, and so our bending moment value is getting a little bit bigger. And so at the 1 meter mark, we finish at negative 1.167 kilonewton meters. The next part, we have to split into two parts. A2 is only 0.25 meters wide, because at the end of A2 we have that direct moment applied. So A2 is going to be that negative 9.167 multiplied by the 0.25. That ends up being negative 2.293, and so we go 2.293 further down on our bending moment diagram. So we add A1 and A2 to get our total of negative 3.46, and then we have to look at that applied moment. In this case, it is 20 kilonewton meters, and it is applied clockwise. And so our direct reaction, shown in blue here, is counterclockwise. That reaction is counterclockwise, and it's the same direction as what we call positive. And so we go up, we go straight up. There is no area because it's applied at that instant point. So we go straight up by 20 kilonewton meters up to 16.54. Making this correlation is key to getting a correct bending moment diagram. And so we continue along to A3, the negative 9.167 times 0.75 meters to get negative 6.875. And we continue along as well for A4. A5 gets a little bit different. It's easy to calculate the area, base times height divided by 2, but the shape of the graph changes. If we think about integrating, if we integrate a flat line, we get a sloped line. If we integrate a sloped line, we get a parabola, an equation of magnitude 2. There's an x squared somewhere in there, so we get a parabola. How do we know which way the parabola goes? The beginning of our triangle, going from left to right, the beginning of our triangle is taller. So if we keep consistent in the width of our rectangles when we split it up, if we're doing if we're going back to integral calculus and we split it up into those really small slices, those really small rectangles, and we keep that the same, the small rectangle on the far left is taller than the small rectangle on the far right. Therefore, our change in area as we go from left to right is getting smaller. And so our parabola is opening this way. It's starting off fast, and then it's going closer to zero. It's slowing down. The slope isn't as steep. Making sure that we get this direction correct is another way to ensure that we have a correct bending moment diagram. When you have both your shear and your bending moment diagrams finished, you pick your, you find your points with your largest magnitudes. So for our shear diagram, it is negative 17.167. For our bending moment diagram, it is 16.54. We take our highest magnitude, and that is the load that we use to calculate our maximum bending stress and our maximum shear stress. I won't be doing that in this video. I'm going to be doing it a little bit later when we get into combined loading and more circle. So we're going to leave it here for now. Yeah, give me feedback, please, on how this is. I know my handwriting is crap, but I try to do this as quickly and as efficiently as I can for you guys.